For centuries, we've looked up and measured the same dark canvas. We charted the stars, named the galaxies, and felt the immense gravity of the known universe. But what if the map we thought was complete had an entire unseen continent waiting to be discovered? Imagine a shift, subtle at first, in the foundational constants of physics, a whisper of energy previously undetectable, an extra dimension quietly influencing everything. We're not talking about another distant galaxy. We're discussing a revelation that changes the very texture of space itself. It's like finding a deeper groove in the vinyl of reality, a track playing a new, profound tune. This isn't theoretical conjecture anymore. It's the moment the lock has clicked. If you appreciate the quiet thrill of scientific breakthrough, the kind of knowledge that settles in and permanently changes your perspective, a soft like and subscribe helps us share these explorations. Settle in with us, because today, the known universe just got a whole lot more complex and a whole lot more fascinating. The universe always holds its deepest secrets in the most subtle movements. For millennia, our understanding of the cosmos was built primarily on light, or what we call electromagnetic waves, the visible spectrum that lets us see stars, and the invisible ones like radio and X-rays that let us measure their energy. But on September the 14th, 2015, something fundamentally changed. A new sense was activated. Scientists working with the Laser Interferometer Gravitational Wave Observatory, or LIGO, directly detected gravitational waves for the very first time. This was not merely confirming a long-held idea. It was like the human race, for thousands of years dependent only on sound, suddenly inventing a machine that could perceive light. Imagine living in a perpetual darkness, relying on touch and hearing, until a device opens up the entire universe, showing us everything from the detail on our own hands to the farthest stretches of cosmic dust. This achievement, which rightly earned the Nobel Prize in Physics in 2017, provided us with a whole new layer of reality. Gravitational waves, like light photons, move at the speed of light, creating subtle ripples across the very fabric of space-time. These signals are everywhere, constantly passing through us. By using the most exquisitely sensitive instruments ever built, scientists are now able to listen for the tremors caused by the universe's most violent and powerful events. We are detecting the final catastrophic moments of colliding black holes, the enormous shockwaves of supernova explosions, and perhaps the signs of exotic phenomena that we have not even begun to imagine. To grasp what LIGO is measuring, we must go back to the basic idea that Albert Einstein introduced in his general theory of relativity. This theory introduced a revolutionary model called space-time, which essentially weaves together the three familiar dimensions of space up, down, and across, with the fourth dimension, time. Any object that has mass fundamentally changes the shape of this space-time. Think of a tight, elastic sheet. If you place a small marble on it, it creates a slight dip. That dip is what we feel as gravity. Now, if you replace the marble with a heavy bowling ball, the dip becomes much deeper. The bowling ball, with its enormous mass, creates far more curvature in the sheet. This curvature is gravity. As these massive objects move through the cosmos, whether they are planets, stars, or black holes, the curvature in space-time shifts position along with them. One of the most mind-bending consequences of this is that when objects with extreme mass accelerate quickly, they become so disruptive that they send actual ripples of gravitational energy outward. These ripples are the gravitational waves. For this to happen, The conditions must be truly cataclysmic. You need unimaginably massive objects undergoing extreme acceleration, such as two neutron stars circling each other just before they merge, or two black holes beginning their final spiral. When such an event occurs, it sends waves of space-time distortion outward in all directions, traveling at the exact same speed as light. You can imagine it as throwing a massive stone into a pond. The resulting ripples spread outward, but instead of moving through water, they are moving through the very structure of reality itself. Just like ripples on a pond, these disturbances become weaker and weaker the farther they travel from their source. When a gravitational wave passes an observer, the distance between all objects would appear to expand and shrink rhythmically. A truly bizarre phenomenon to try and visualize. Despite predicting their existence in his theory, Einstein himself believed that we would never be able to detect them. He thought the resulting disturbances would be too impossibly small to ever be measured by human technology. And for good reason. The change in distance that LIGO is designed to detect is unbelievably tiny. It is 1/10,000th the length of a single proton. Let that sink in for a moment. We are talking about signals that are 10,000 times smaller than a fundamental particle that is already microscopic. Yet, embedded within these nearly imperceptible signals is a vast amount of information about the universe. They carry data detailing when and where they originated, how far they traveled across the cosmos, and precisely what kind of event a supernova or a black hole collision produced them. This incredible feat of detection is made possible by LIGO. It is not a single instrument, but a system of two enormous observatories, both located in the United States. They were funded by the National Science Foundation and are managed collaboratively by two major institutions, the Massachusetts Institute of Technology, or MIT, and the California Institute of Technology, or Caltech. The success of the Laser Interferometer Gravitational Wave Observatory stands on the shoulders of giants. Among its driving scientific forces were the physicists Kip Thorne, Rainer Weiss, and Barry Barish, all of whom shared the 2017 Nobel Prize for their decisive and fundamental contributions to making this detection possible. LIGO itself is, at its core, a large-scale, intensely sensitive interferometer. The concept of an interferometer has actually been around since the 1880s, serving as a clever tool to measure subtle properties of light. An interferometer works by taking light waves from two or more sources and combining them. The key is in seeing how the waves interact with one another. For example, if you wanted to test whether light travels at different speeds through different materials, perhaps through air versus through a denser fluid like water, an interferometer would show you the answer. Even a microscopic difference in the speed the light travels will produce an interference pattern when the two waves finally meet. Think of it just like the ripples on a calm pond. If the crest, or the high point, of one ripple happens to perfectly meet the trough, or the low point of a second ripple, they will completely cancel each other out. This subtracts their energy, and the water will immediately become flat again at that exact spot. Conversely, if the crest of one wave lines up exactly with the crest of the other wave, the two waves are said to be in phase, and their height and energy will combine, adding to each other. This is precisely what the light sensor inside the interferometer measures. By analyzing how in or out of phase the two light waves are when they combine, scientists can infer the tiniest relative differences in the speed or the distance the light beams traveled. The simple rule for interferometry, especially for something trying to detect a disturbance smaller than a proton, is that bigger is better, meaning the larger the scale of the instrument, the more sensitive it becomes to minuscule changes. This is how the massive scale of LIGO becomes essential. The system is made up of two distinct and identical observatories, strategically placed thousands of miles apart in the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. The reason for having two sites is purely mathematical and logical. You need at least two locations to triangulate and confirm where the signal actually came from, proving that the ripple was a real event passing through Earth and not just localized noise. At each of these observatories, a powerful laser is continuously fired. This laser beam has to operate at around 750 kilowatts of power, an energy level intense enough to vaporize anything that strays into its path. The laser first strikes a beam splitter, a special mirror positioned at a 45-degree angle. This splitter immediately divides the incoming laser beam into two separate beams, sending them off at a perfect right angle to one another. These two light beams then begin their journey down two arms that form an L shape. Each arm is a 4-kilometer vacuum cavity, meaning the air has been aggressively pumped out. At the end of each 4-kilometer arm sits a highly polished mirror. The beams bounce off this main mirror and then bounce repeatedly between it and a second mirror, called a recycling mirror, which sits near the beam splitter. The light travels back and forth nearly 300 times within the 4-kilometer arm. This process dramatically increases the effective distance the light travels from 4 kilometers to a staggering 1,200 kilometers. Remember the rule: the greater the distance traveled, the more sensitive the measurement. After completing their nearly 300 trips, the two laser beams meet back at the beam splitter and are directed toward a specialized light-sensitive detector called a photodiode. In a perfect, quiet universe, the two beams would have traveled the exact same distance and, therefore, would arrive at the photodiode perfectly in phase. Being perfectly in phase means their crests and troughs align and cancel each other out completely, just like the ripples on the pond. As a result, no light would reach the photodiode. This dark state is LIGO's perfect baseline. But when a gravitational wave passes through the observatory, the very fabric of space-time around the arms is briefly stretched and squeezed. This distortion makes the length of the two 1,200-kilometer paths infinitesimally different. Because the beams have traveled different distances, they become slightly out of phase when they recombine. When they are out of phase, they no longer completely cancel each other, and a minuscule flash of light appears and hits the photodiode. This flash is the physical signal, indicating the presence of a gravitational wave. The challenge is that the real world is far from perfect. The interferometer is constantly picking up noise from countless sources: seismic activity, passing traffic, temperature changes, and even the faint internal vibrations of the equipment itself. To mitigate this noise, LIGO uses incredibly smooth, highly engineered mirrors, each weighing 40 kilograms, which are suspended by delicate fibers made of fused silica. The vacuum inside the 4-kilometer arms must also be nearly perfect. Any tiny particles of air or dust would be a serious problem for the light beams. This is why LIGO pumps the air out of its vacuum chambers until the pressure is reduced to only 1/trillionth of the pressure of Earth's atmosphere at sea level. However, even when all the major environmental noise is accounted for, another, deeper problem remains. At the subatomic level, the level needed to measure a disturbance smaller than a proton, the laws of quantum mechanics introduce unavoidable randomness into how photons, the particles of light, behave. This randomness in the light itself acts as a fundamental limit, or a form of noise. LIGO's solution to this is nothing short of brilliant: a an optical cavity that effectively squeezes the light. This process is highly technical, but the result is beautifully simple. It minimizes the noise related to the phase of the light, which is what the interferometer measures, and instead shifts that inherent quantum randomness into the amplitude noise, which relates to the height of the waves, something the instrument is deliberately designed not to measure. Think of quantum randomness as the inevitable clutter in your life. You cannot eliminate the mess completely. It's a fundamental fact of physics at that level. But you can strategically move that clutter from the center of your living room floor, where it interferes with your daily path, into a closet where it is hidden and out of the way. The chaos hasn't vanished, but it has been shifted so that it no longer corrupts the signal. The ultimate goal of LIGO is not to achieve absolute silence, which is physically impossible. The goal is to maximize the signal-to-noise ratio to ensure that the flash of light created by a passing cosmic ripple is undeniably louder than the background hum of the entire universe, proving that what we have detected is a genuine wave of space-time. The initial successes of this new gravitational listening ability have already redefined the scale of cosmic power. The very first signal detected by LIGO in 2015, famously labeled GW150914, gave us an immediate and dramatic example of this new layer of the universe. Scientists analyzed the data from that moment and confirmed it was caused by the merger of two enormous black holes located approximately 1.66 billion light-years away from us. These two black holes, one measuring 36 solar masses and the other 29 solar masses, had been orbiting each other as a binary system for countless ages. In the final, catastrophic 20 milliseconds of their spiral, they slammed together and combined their masses. The resulting release of pure energy was so powerful, it is almost impossible to comprehend. The scientific consensus is that the energy released in that brief fraction of a second was 50 times the combined light output of every single star in the entire observable universe. It is a number that defies intuition and proves just how violent and powerful the unseen fabric of space-time can be. Yet, after traveling across 1.66 billion years of space, finally reaching our planet, the disturbance was so incredibly faint that it only moved the 4-kilometer arms of the LIGO detectors by an amount equal to 1/10,000th the width of a single proton. To visualize this level of precision, imagine the vast, impossible distance between Earth and our nearest star system, Proxima Centauri. Now, imagine that distance briefly changing by the thickness of a human hair. That is the staggering, almost unbelievable level of sensitivity and precision that LIGO achieved to detect its first signal. This initial success is widely considered one of the most astonishing technological feats in the entire history of human engineering. That first detection was merely the beginning. Just 3 months later, in December 2015, LIGO recorded a second signal, again originating from a distant black hole merger approximately 1.4 billion light-years away. This quickly confirmed that the first detection was not a fluke, but the opening of a permanent new window onto the cosmos. Over its initial 3 operational runs, the LIGO system has recorded well over 80 black hole mergers. Each detection provides new data points about the size, frequency, and distribution of these elusive objects, painting a picture of a far more dynamic and crowded universe than previously assumed. Then came another monumental breakthrough in August 2017. LIGO detected the merger of 2 neutron stars, an event labeled GW170-817. This signal was significant because it was the first gravitational wave event to be independently confirmed by traditional electromagnetic observations. More than 70 observatories around the planet, including ground-based telescopes and space telescopes, were able to pivot and observe the electromagnetic light and gamma rays emitted by the same event seconds after the gravitational wave passed. This moment signaled the true birth of multi-messenger astronomy, where we no longer rely on light alone, but combine gravity, light, and potentially other messengers, like neutrinos, to understand a single cosmic event. This holistic approach provides a richer and more complete view of the universe than ever before possible. For its first 3 operational runs, LIGO was essentially just warming up. Following its initial period of astounding success, the observatories went offline for a 3-year period to undergo massive upgrades. As of May 2023, LIGO has begun its highly anticipated 4th operational run, with even greater sensitivity. The upgrades included using more reflective mirrors, implementing a system of better mirror suspension to further isolate them from the slightest vibrations, and most importantly, refining the light-squeezing technology to reduce the fundamental noise caused by quantum uncertainty. These improvements ensure the instrument is now even more likely to hear the most distant and quietest signals. Crucially, in this new operational run, LIGO is working in collaboration with a 3rd global partner, KAGRA. KAGRA is a new interferometer observatory located deep underground in Hida, Japan. Its underground location makes it the world's first subterranean gravitational wave observatory, providing additional isolation from seismic noise. KAGRA also pioneers the use of cryogenic mirrors, chilling its mirrors down to extreme temperatures to minimize the thermal vibration noise. The addition of KAGRA significantly improves the overall detection network, with 3 sites working together: Hanford, Livingston, and KAGRA. The ability to triangulate the precise location of a cosmic event becomes far more accurate and reliable. Early signs from an engineering run in May 2023 are already proving promising, with scientists reporting a possible signal caused by a neutron star being swallowed by a black hole. While this detection requires time for confirmation and analysis, if these early results hold, the 4th run is set to dramatically expand our understanding of how these powerful events shape the cosmos. Looking further into the future, the global effort to listen to gravity is accelerating rapidly. The country of India is preparing a major collaborative project called LIGO India, or Indigo. This new observatory will provide a 4th global site, creating a powerful, widely separated network that will allow for near-perfect triangulation and location mapping of gravitational sources across the sky. On the technical front, LIGO itself has a major upgrade planned for the years 2027 to 2028, known as the LIGO Voyager upgrade. This ambitious plan will replace the existing components with technology designed for even higher sensitivity. This includes using mirrors that are 4 times heavier than the current 40-kilogram versions and incorporating new laser systems that operate at higher frequencies. These changes are expected to push the instrument's sensitivity to an entirely new level. Beyond these near-term upgrades, scientists have proposed plans for a 3rd-generation facility, tentatively named Cosmic Explorer. This facility would be built as 2 new observatories, featuring arms that span an unimaginable 40 kilometers and 20 kilometers respectively. This proposal firmly adheres to the rule that for interferometers, bigger is always better, promising a sensitivity level that could detect signals across the entire history of the universe. However, the proposal that truly captures the imagination is the Laser Interferometer Space Antenna, or LISA. This would be the world's first space-based gravitational wave observatory. LISA will consist of 3 separate spacecraft flying in formation millions of kilometers above Earth. These craft will create a giant triangle in space with arms extending 2.5 million kilometers long. This space-based interferometer would be so immense and so precise that scientists hope it will be adept at uncovering the most exotic and theoretical sources of gravitational waves. This includes the possibility of detecting the echoes from events like cosmic strings, which are highly speculative wrinkles in the fabric of space-time, and other phenomena that have only ever been discussed in theory. In essence, LISA's goal is to help us stare directly into the fundamental texture of reality. With a planned launch date of 2037, we are still over a decade away, but the potential of this mission is revolutionary. The ability to detect gravitational waves gives us evidence of extremely remote and ancient phenomena that cannot be measured by any other means, allowing us to peer into the universe's earliest, most violent moments. Furthermore, gravitational waves serve as a crucial secondary observation tool, verifying and complementing observations made by electromagnetic instruments like the Hubble or the James Webb Space Telescope. In time, this entirely new field of gravitational wave astronomy should allow us to fully understand the nature of our universe, charting its complete history and perhaps even predicting its future. We are learning to tune into the cosmos with the right equipment, and the result is hearing the universe humming no matter where we look in the sky. Of course, sound as we know it cannot travel through the vacuum of space. Instead, this hum is the sound of gravitational background noise, a faint echo of all the black hole mergers and violent cosmic collisions that have ever taken place since the beginning of time. You may already be familiar with a similar background signal discovered decades ago, the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang itself. This background of microwave light was a groundbreaking discovery. It was the smoking gun that cemented the Big Bang as the leading theory for the universe's origin. Yet, this light signal has a glaring weakness. Despite being the earliest light we can see, it was only emitted nearly 400,000 years after the Big Bang occurred. To see what happened before that moment, the very, very beginning, we need a background signal made not of light, which took time to travel, but of the fundamental ripples of the fabric of space-time itself. The cosmic microwave background, CMB, while groundbreaking, serves as a curtain that obscures the first 400,000 years of the universe's life. If we truly want to peer into the primordial soup, the period immediately following the Big Bang, we need a signal made of gravity, which was unaffected by the thick, charged plasma that blocked the early light. That ultimate gravitational signal is believed to exist as a low, persistent hum of space-time. In 2023, a group of astronomers working on the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, announced a potentially revolutionary finding. Using an incredibly clever and resourceful technique, they may have detected exactly this background hum. Instead of relying on gigantic, earthbound tunnels like LIGO, these scientists have turned exotic stars themselves into a galactic-sized gravitational wave detector, allowing them to measure the faint, collective vibration of space-time. This persistent hum of gravitational waves might well be the deep reverberation of the universe's earliest moments, resonating across all of space. To understand the genius of the nanograv approach, we must first recognize the limitations of the current technology. We previously discussed the LIGO detectors, which use powerful lasers bounced along 4-kilometer vacuum tunnels to precisely measure the minuscule stretching and squeezing of space-time as a gravitational wave passes through. This distortion causes tiny changes in the time it takes for the light to complete its round trip. However, like all waves, gravitational waves exist across a broad spectrum of frequencies. Think of music. You have high notes, low notes, and everything in between. LIGO is exquisitely sensitive, but it is effectively only listening to the high-frequency end of this cosmic orchestra. The high-frequency waves that LIGO detects are generated by catastrophic, fast-paced events like stellar mass black holes rapidly spiraling inward and colliding in the final, dramatic bang that can involve hundreds of orbits per second. This focus on high frequency is also why LIGO cannot detect the signals from the much earlier, slower stages of these same binary systems. When massive objects are orbiting each other at a great distance, their orbits are incredibly slow. They might take months or years to complete a single loop. These slow orbits generate gravitational waves that have a much lower frequency and therefore much lower individual energy. If the high-frequency events are like sudden claps of thunder, these low-frequency events are not bangs at all. They combine into one collective, steady, ambient hum that permeates the cosmos. The greatest contributors to this low-frequency background hum are not the smaller black holes that LIGO detects, but the supermassive black holes found at the centers of nearly all galaxies. These behemoths can be millions or even billions of times the mass of our Sunday pairs. Of these supermassive black holes only form when something truly spectacular occurs in the universe, the merger of two galaxies. When two galaxies collide, the vast majority of the stars, planets, and gas clouds simply pass through each other because of the enormous amounts of empty interstellar space between them. Actual collisions of individual stars are exceedingly rare. However, the collective gravitational forces pull the galaxies together, causing them to merge over billions of years into a single, larger galaxy. Crucially, the nuclei of these merging galaxies, the two supermassive black holes, do not merge instantly. Instead, they begin to orbit each other, forming a supermassive black hole binary. These binaries continue their slow, majestic dance long after the surrounding stellar structures have settled into a single, unified galaxy. These long, slow orbits generate the lowest, deepest gravitational waves, specifically in the nanohertz range. The nanohertz range refers to waves so slow that their period, the time it takes for one complete cycle, is measured in years. Just as the human ear cannot perceive ultra-low frequency sound waves which can make a loud tremor feel like a silent vibration, LIGO is deaf to this nanohertz cosmic symphony. This is where the Nanograv collaboration stepped in. To listen to waves that take years to cycle, you need an instrument with an arm length measured not in kilometers, but in thousands of light years. The astronomers at Nanograv realized that the universe had already built the perfect low-frequency detector for them: pulsars. A pulsar is a special type of neutron star, the hyperdense, rapidly spinning remnant of a massive star explosion. These pulsars emit incredibly stable beams of radio waves from their magnetic poles, much like a cosmic lighthouse beam. As the star spins, these beams sweep across Earth, creating highly regular, almost perfectly timed pulses. The timing of these pulses is often more precise than the best atomic clocks on Earth. The Nanograv team selected an array of 68 highly stable pulsars distributed across our Milky Way galaxy. They meticulously monitored the timing of the pulses from these stars for over 15 years, creating what is known as a pulsar timing array, or PTA. This PTA acts as a massive, galaxy-spanning interferometer. If a low-frequency gravitational wave passes between the Earth and one of these pulsars, it causes the very space-time between them to stretch and contract. When space-time stretches, the pulse has a slightly longer distance to travel to Earth, making its arrival time slightly delayed. When space-time contracts, the distance is briefly shortened and the pulse arrives slightly earlier. The effect is incredibly subtle. The gravitational waves in the nanohertz range are so weak that they might change the distance to a pulsar, which could be thousands of light years away, by only a few hundred meters, a tiny fraction of that enormous distance. Yet the pulsars are such precise clocks that this change in distance translates into a detectable difference of mere tens or hundreds of nanoseconds in the pulse arrival time over the course of a year. The trick is distinguishing this gravitational wave signal from all the other sources of noise. The arrival time of a single pulsar pulse can be affected by everything from instrumental error to the slow drift of plasma in interstellar space. The key is finding a signal that is correlated across all 68 pulsars. A gravitational wave passing through the galaxy does not affect just one pulsar. It affects the space-time between Earth and every pulsar simultaneously. Therefore, the researchers looked for a quadrupolar signature, a specific pattern in the timing delays. As the wave passes, it might delay the pulses from pulsars in one part of the sky, while simultaneously speeding up the pulses from pulsars in the opposite part of the sky. This characteristic pattern, a collective wobble shared by all 68 highly stable clocks, is the definitive proof of the nanohertz gravitational wave background. In their 2023 announcement, Nanograv confirmed they had detected strong evidence of this correlated signal in their dataset. The data shows a persistent, low-frequency hum that is remarkably consistent with the expected noise generated by the mergers of billions of pairs of supermassive black holes scattered across the universe. If confirmed, this is an immense scientific milestone that provides a completely new way to study the largest structures in the cosmos. Listening in on this cosmic cacophony gives us unprecedented insight into how galaxies merge and how supermassive black holes grow and interact over cosmic time. But perhaps the most exciting prospect of detecting the gravitational wave background is that it is a direct window into the very first moments of our universe's existence. The standard Big Bang model predicts that during the universe's rapid inflation phase, fundamental quantum fluctuations were stretched into massive ripples, generating a primordial gravitational background noise. This noise would also fall into the nanohertz frequency range. If the hum detected by Nanograv contains contributions from this primordial background, we will have effectively peered through the light curtain of the cosmic microwave background and looked back further than ever before. We would be listening to the literal tremors of the universe's creation, hearing an echo of the cosmos less than a second old. The ability to detect these waves using objects as stable and distant as pulsars transforms our galaxy into a single, vast physics laboratory. The core physical challenge in detecting the universe's background gravitational hum lies entirely in the problem of scale. We have established that the frequency of any wave, be it sound, light, or gravity, is inversely related to its wavelength. This means that a faster, more rapid wave has a shorter length, and a slower, more deliberate wave must stretch out over a greater distance. To better grasp this fundamental concept, consider the common spectrum of sound. High-frequency sound waves, like the quick, sharp chirp of a small bird or the sudden smash of a cymbal, possess a very short wavelength and cycle rapidly. Because of this short length, you can easily detect and hear the change in the sound wave over a very small, short distance. In contrast, Low-frequency sound waves, such as the deep, throaty rumble of a massive pipe organ or the distant roar of a volcanic tremor, have an incredibly long wavelength and cycle very slowly. To truly perceive the entire, vast power of that low note, to fully feel the wave rise and fall, you need to be far enough away for the entire, elongated wave to sweep past your ears. The nanohertz gravitational waves we are seeking are the ultimate, extreme example of this low-frequency phenomenon. Recall the waves that detectors like LIGO are designed to hear. The high-frequency waves generated by stellar mass black holes colliding. These waves cycle hundreds of times per second and have wavelengths measured in mere thousands of kilometers. Nanohertz waves, however, are generated by the much slower, grander dance of supermassive black hole binaries, the cores of merging galaxies. A single cycle of stretching and squeezing caused by a nanohertz wave takes an immense amount of time to fully complete, approximately 1 billion seconds. This is the cosmic equivalent of a note so low it lasts for more than 31 years. Since these gravitational waves still travel at the speed of light, approximately 300 million meters per second, and since a single oscillation takes over 30 years, the resulting wavelength is astronomical. These waves are not measured in simple meters, or even the distance from Earth to the Sun. They are measured in tens of light years long. This means the crest of the wave might be passing through the solar system while the trough is still many light years away in interstellar space. The constraint this places on physical engineering is absolute. To build a traditional, ground-based detector, large enough to observe even one full cycle of stretching and squeezing, and to properly use the principle of interference, the arms of the instrument would need to span distances far greater than the entire reach of our solar system. Constructing a vacuum tunnel tens of light years long is fundamentally impossible. This is precisely why the only feasible detector for these colossal, ultra-low frequency waves is the pulsar timing array. The PTA utilizes the immense existing distances between Earth and a carefully selected set of pulsars scattered across our galaxy. This collective arrangement transforms the vast expanse of space itself into the necessary, light-years-long interferometer arm. The core mechanism is rooted in the perfect, clockwork timing of pulsars. A pulsar is a rapidly spinning, hyperdense remnant of a massive star explosion that emits incredibly stable beams of radio waves. These beams sweep across Earth, delivering a series of pulses with a precision often exceeding our best atomic clocks. The PTA, consisting of dozens of these celestial clocks, acts as a distributed gravitational sensor. When an immense nanohertz gravitational wave passes between the Earth and one of these pulsars, it causes the fabric of spacetime along that path to briefly stretch and contract. When spacetime stretches, the radio pulse must travel a slightly longer distance, making its arrival time on Earth minutely delayed. When spacetime contracts, the distance is shortened, and the pulse arrives slightly earlier. This minute difference in arrival time, sometimes only a few tens of nanoseconds over a year, is the interference pattern that Nanograv meticulously analyzes. The genius is that the scientists are not looking for a timing fluctuation in just one pulsar, which could be noise. They are looking for a collective, correlated wobble across all 68 pulsars. As a gravitational wave sweeps through our galaxy, it affects the space-time paths of all pulsars simultaneously, creating a specific, recognizable signature known as the quadrupolar correlation. This unique pattern, where pulses from one part of the sky are systematically delayed, while pulses from the opposite part of the sky are simultaneously sped up is the definitive proof that the Earth is not simply wobbling due to local errors, but is truly bobbing up and down in the low, persistent hum of space-time itself. This makes the Milky Way, thanks to the inherent stability of its pulsars, the world's most massive and sensitive gravitational wave observatory. This galactic-scale observatory, however, relies on far more than just the immense distances between its components. Its ultimate success hinges on the clockwork precision of its stellar beacons. Each pulsar is a special type of neutron star, the compressed, rapidly spinning remnant left behind after a massive star runs out of fuel and collapses. These objects possess such powerful magnetic fields that they emit narrow, focused beams of radio waves from their poles. As the pulsar spins, these beams sweep across the cosmos like a lighthouse in the dark. When one of these beams sweeps across Earth, we receive a sharp, consistent burst of energy, or a pulse. The regularity of these pulses is astonishing. Many pulsars are more stable and reliable than even the most meticulously maintained atomic clocks we have on our planet. This consistency is the core asset of the pulsar timing array. The 68 pulsars selected by the Nanograv collaboration are not just randomly chosen stars. They are the most stable, reliable cosmic timers available, effectively turning the entire Milky Way into a single, cohesive, and highly sensitive scientific instrument. The physics behind the detection is a direct application of the interferometer principle, but applied over light-year scales. When a nanohertz gravitational wave passes through the vast expanse between Earth and one of these distant pulsars, it causes a minute, but critical, disturbance. The wave briefly stretches and compresses the very space-time connecting the 2 points. If space-time stretches along the path, the radio pulse has a slightly longer distance to travel to reach us, causing its arrival time to be delayed. If space-time is compressed, the distance is briefly shortened, and the pulse arrives slightly earlier. This tiny, measurable change in the pulse arrival time, often only tens of nanoseconds over the course of an entire year, is the interference pattern that astronomers are hunting for. However, the universe is full of interference. A single timing fluctuation in one pulsar could be caused by almost anything. A subtle error in the telescope equipment, the passage of interstellar plasma turbulence, or even unknown wobbles in the pulsar itself. To eliminate these local sources of noise and confirm the presence of a true gravitational wave, astronomers must detect a specific, universal pattern that affects all pulsars simultaneously. This specific pattern is the quadrupolar correlation, the unique fingerprint of a gravitational wave, as predicted by Albert Einstein's theory of general relativity. A gravitational wave does not simply compress space-time uniformly. It distorts it in a specific, elegant way. Imagine space-time being stretched along one axis, like the north-south axis, while being simultaneously compressed along the perpendicular axis, like the east-west axis, as the wave passes. This means that if the pulses from a set of pulsars in one direction of the sky, for example, those aligned with the stretching axis appear to be arriving later than expected, the pulses from a corresponding set of pulsars in an entirely different region of the sky, aligned with the compression axis, should simultaneously appear to arrive earlier. This collective synchronized wobble, where the timing fluctuation is observed in all 68 pulsars and precisely follows this theoretical quadrupolar pattern, is the definitive, undeniable proof. It is the signature that confirms what they are observing is the actual nanohertz gravitational wave background passing through our galactic neighborhood. The confirmation of this pervasive background signal as announced by the nanograv collaboration, is not merely a technical triumph. It immediately opens two distinct and monumental chapters in astrophysics. We are gaining insight into two of the universe's most extreme phenomena: the fate of the largest black holes and the very creation of space-time itself. The first chapter, opened by the detection of the nanohertz hum, is the sweeping, complex story of supermassive black holes. For decades, the dominant source of this low, persistent gravitational noise has been predicted to be the combined effect of countless pairs of supermassive black holes orbiting one another across the universe. These gargantuan black holes, each containing the mass of millions or billions of suns, reside at the core of nearly every massive galaxy. The only way for two such giants to form a pair is through the merger of two entire galaxies. Until the nanograv detection, our evidence for these supermassive binary systems was almost entirely indirect. We could observe two galaxies colliding and settling into a single, merged entity, and based on our gravitational physics, we knew that the two central black holes must be spiraling toward each other, driven by the intense force of gravity. However, charting this immense, slow-motion orbital dance was impossible. We lacked the tool to listen to their movement. The gravitational hum changes everything. This deep, persistent noise is the collective, unending song of all these black hole pairs, singing their way across the eons toward their inevitable collision. By meticulously analyzing the precise characteristics and strength of this cosmic hum, scientists can begin to answer some of the most profound, long-standing questions about galaxy evolution and the growth of cosmic structure. One primary question concerns frequency and efficiency. How frequently do massive galaxies actually merge in the cosmos? And when they do, how quickly do their central black holes find each other and commence their mutual orbit? The strength of the detected background hum provides a direct measure of the population density of these supermassive binaries. A louder hum means more pairs, and therefore a higher rate of massive galaxy mergers throughout cosmic history. A more challenging and critical question centers on the mechanisms that eventually force these enormous black holes to finally slam together. Theoretical models suggest that once two black holes get relatively close, within about 1 parsec of each other, they should struggle to shed the remaining orbital energy needed to merge. This theoretical barrier is famously known as the final parsec problem. If they stop shedding energy, they stall, and the merger never happens. The nanohertz hum provides the direct evidence needed to test this obstacle. The frequency and slope of the observed hum directly tell us how quickly these binaries are shrinking their orbits. If the hum is stronger than expected at certain frequencies, it confirms that some mechanism, perhaps interaction with the surrounding stars and gas, or a third black hole intervention, is efficiently solving the final parsec problem, ensuring that these colossal mergers do occur. The characteristics encoded in the hum will provide the first hard, observational data that either confirms or denies various proposed solutions to this problem, offering a new, dynamic map of how the most massive structures in the universe are born, grow, and evolve through violent gravitational interactions. The hum is essentially providing the timing track for the universe's slowest, grandest gravitational ballet. The second chapter, and perhaps the most thrilling, is the quest for primordial gravitational waves. If the nanograv hum contains more energy than can be accounted for by the supermassive black hole binaries alone, the excess energy must come from an earlier, more fundamental source: the universe's inflationary epoch. The leading cosmological model the inflationary theory, posits that immediately following the Big Bang, the universe underwent a period of rapid, exponential expansion that lasted for only a tiny fraction of a second. This inflationary period was so violent that it took the minute fundamental quantum fluctuations that existed at that instant and stretched them to a cosmological scale, creating enormous, permanent ripples in space-time. These are the primordial gravitational waves. If these waves exist, they have been stretched and redshifted by the expansion of the universe for almost 14 billion years, and they are expected to fall precisely within the same low-frequency, nanohertz range as the black hole binaries. Detecting them would provide direct, observational proof of the inflationary theory, an idea that has been central to cosmology for decades, but has lacked direct evidence. Furthermore, a detection could help us distinguish between the inflationary theory and alternative models, such as those involving cosmic strings. Cosmic strings are hypothetical, one-dimensional faults or defects in the fabric of space-time, much like cracks that might form when water freezes into ice. If these cosmic strings exist, their rapid oscillation and movement would also generate a gravitational wave background, but one with a slightly different characteristic shape than the background predicted by inflation. By meticulously analyzing the exact shape and slope of the nanohertz hum, whether it is a smooth, gentle rise characteristic of inflation or a steeper, more complex curve characteristic of cosmic strings, astronomers could directly test the fundamental physics that governed the universe when it was less than a second old. We would effectively be using the gravitational waves to listen for the physics of creation. This ability to peer through the curtain of the CMB and listen to the literal tremors of the universe's birth represents the ultimate goal of gravitational wave astronomy, understanding the moment where time and space truly began. The ability to probe the universe when it was less than a second old by listening for primordial gravitational waves represents the ultimate goal of gravitational wave astronomy, understanding the moment where time and space truly began. To achieve this, however, required astronomers to overcome the impossible engineering problem of scale. Clearly, we cannot construct a detector suitable for this task on Earth, or even within the confines of our solar system. The sheer size of the nanohertz wavelength demands technology that extends far beyond our current stellar neighborhood. Instead of waiting for humanity to ascend beyond our solar system and become a multi-generational spacefaring civilization capable of building massive orbital structures, astronomers at the Nanograv collaboration utilized an ingenious solution. They employed a clever observational trick, turning existing astronomical phenomena into the required cosmic scale instrument. The core of this trick is the pulsar. You may recall our previous discussion about pulsars and the immense stability of these ultra-dense neutron stars. These celestial objects, born from the collapse of massive stars, spin with remarkable stability. They emit highly focused beams of radio waves from their magnetic poles. As the neutron star rotates, these colossal beams of radio waves sweep across space, striking Earth again and again, delivering highly predictable pulses. The pulses arrive with such precise certainty that they are universally used as the most reliable clocks in the cosmos, capable of keeping time accurately across vast astronomical distances. Therefore, by carefully selecting and continuously monitoring already identified pulsars, we can rely on them to supply us with incredibly reliable timing signals from thousands of light years away. The pulsars function, in essence, like the perfectly reflective mirrors at the end of the long arms of a LIGO-style interferometer. The key difference is that instead of reflecting a signal we sent out, they are generating their own perfectly timed signal back to us. Nanograv has effectively concocted a functional, imaginary interferometer that stretches for thousands of light years. And all we need to use this magnificent cosmic instrument are the relatively simple radio telescopes that humanity has been using for decades. The success of this imaginary interferometer hinges on the quality and stability of the data. Our final calculations, our final certainty will only be as good as the observations we gather. When choosing pulsars to observe, astronomers must rigorously ensure that they are uniquely suited for the demanding task of acting as a clock in space-time. The best candidates are handpicked and added to a specific group called a pulsar timing array. For the Nanograv experiment, the final array makes use of 68 pulsars, each chosen for a specific set of special properties that maximize the chance of detecting the gravitational hum. First, they had to be spread strategically across the entire sky. This wide distribution ensures that we can gauge how these massive, light-year-long gravitational waves are affecting the fabric of space-time in all directions simultaneously, providing the necessary spatial data for the quadrupolar correlation. Second, the chosen pulsars had to be millisecond pulsars, meaning they complete hundreds or even thousands of rotations every single second. As we discussed previously, these fast-spinning pulsars are expected to be the most stable and dependable when it comes to the regularity of their pulses, maintaining a timing certainty that even rivals that of some earthbound atomic clocks. We could not ask for better, more widely distributed timekeepers to be dotted across the turbulent sea of space and time. This extreme regularity is crucial. It means that astronomers can take highly precise measurements of the time their pulses arrive and continue taking these measurements over the course of multiple years in Nanograv's case, more than a decade, to see if any lasting, underlying changes are occurring in the space-time between us and the pulsar. Of course, the measured times of arrival will naturally vary due to all sorts of factors. The most predictable factor is the simple change in distance between the Earth and the pulsar as both objects continue moving along their orbits around the center of the galaxy and the Sunday. However, scientists can easily account for this through well-established, precise orbital mechanics. More challenging are the less predictable factors that introduce random noise into the data. For instance, random fluctuations in the interstellar gas, the thinly spread matter between the stars, can cause tiny, unpredictable delays in the radio signal that are not related to the stretching of space-time. How do scientists effectively remove this overwhelming noise from pulsars located thousands of light years away? The answer lies in statistics and the very nature of a gravitational wave. Just like LIGO, a single, isolated tunnel is never sufficient for a reliable measurement. We need to create multiple pairs of imaginary tunnels, or in this case, multiple pairs of pulsars. Random noise, such as interstellar gas turbulence, is uncorrelated. The random delay experienced by the signal from one pulsar is highly unlikely to match the random delay experienced by a second, widely separated pulsar. However, if similar fluctuations show up simultaneously in two entirely separate pulsars, it is extremely improbable that the random noise simply aligned by chance to make it appear they are acting in unison. It is far more likely that there is a common cause underlying both fluctuations, the most likely candidate being the photons from both pulsars riding the same gravitational wave that is washing over them both. The key to distinguishing the true gravitational wave background from the universe's inherent noise lies in the power of statistics and correlation. Since random noise such as fluctuations caused by interstellar plasma or instrumental errors is uncorrelated across large cosmic distances, the technique used by the nanograph team was to analyze the statistical relationship between every pair of pulsars in their pulsar timing array. The core idea is to see if the timing fluctuations of one pulsar match up or correlate with the fluctuations of another pulsar. Astronomers plot this correlation strength against the angular distance separating those pulsar pairs in the sky. If the universe were truly silent in the nanohertz range, meaning there was no underlying gravitational wave background noise, then the timing variations from different pulsars should be completely independent of one another. The random fluctuations experienced by one pulsar should have no relationship to the random fluctuations experienced by another, thousands of light years away. If one were to graph this scenario, the plot of correlation against angular separation would show a straight line right at the level of zero. However, the presence of a pervasive background gravitational wave signal imposes a specific, predictable structure onto these correlations. A gravitational wave is a global phenomenon. It affects the space-time between Earth and every pulsar simultaneously, but in a patterned way. The theory of general relativity dictates exactly what this pattern must look like. When the measured data is plotted, the gravitational wave signal should not show a straight line, but rather a special, curved line known as the Hellings and Downs curve. This curve mathematically dictates the exact correlation strength that must be expected between any two pulsars, based solely on their angular separation in the sky. It is the defining, hallmark signature of a quadrupolar gravitational wave. Background waves that stretch along one direction, like the line connecting a closely spaced pair of pulsars, while simultaneously squishing in the perpendicular direction, like the line connecting a widely separated pair. The specific shape of the curve proves the waves are gravitational in nature, rather than some other form of cosmic noise. This sophisticated analysis is precisely what the nanograph collaboration, alongside its international partners, succeeded in achieving. It was a massive undertaking, relying on over 15 years of continuous, painstaking timing observations of their 68 pulsars. The accumulation of this immense dataset, gathered by radio telescopes around the world, finally provided the statistical power necessary to silence the noise and reveal the true signal. On the 28th of June, 2023, the team made a historic announcement. Their plotted data perfectly followed the theoretical predictions of the Hellings and Downs curve. This curve was the definitive graph the scientific community had been waiting for, the final piece of evidence to confirm that the observed variations in pulsar timing were indeed caused by a nanohertz gravitational wave background washing over our galaxy. It was a momentous scientific breakthrough achieved without the need to build a single new piece of exotic hardware in space, instead leveraging the intrinsic physics of the universe. The statistical weight of this evidence was crucial. The researchers calculated that the data showed the existence of this gravitational wave background was statistically significant at the 3 sigma level. This measurement indicates that there is only about a 1 in 1,000 chance that this result is a mere false alarm, that the observed curve was the result of random statistical chance or unpredicted background noise. In the realm of physics, a 5 sigma level is generally considered the absolute gold standard for an official discovery, effectively making the chance of error 1 in 3.5 million. However, the 3 sigma result is still exceptionally strong evidence, marking this achievement as a powerful indication of reality and a major step forward. As the collaborations continue to collect and analyze more data over the coming years, they will be able to refine their timing models, reduce the size of the error bars in their plots, and eventually move toward the final, universally accepted 5 Sigma official announcement of a cosmic discovery. The hum has been found. Now, the work begins to turn that hum into a precise song. The detection of the gravitational wave background marks the successful end of one long chapter and the immediate opening of 2 new profound chapters in our understanding of the universe. The hum is a collective noise, and while we cannot currently pick apart the individual sources of this chaotic sound, the overall volume and shape of the hum holds secrets to the cosmos's most extreme events. The nanohertz hum provides a direct observational tool to study supermassive black hole binaries. This is a chance to move beyond the background noise and, through increasingly sensitive analysis, eventually allow us to listen to specific, distinct supermassive black hole binaries, the loudest singers in the cosmic choir. By separating these individual signals from the background, we can directly measure the orbital decay of these colossal pairs, solving the long-standing final parsec problem and mapping the entire evolutionary history of galaxies. Most significantly, the background hum is the first observational window into the universe's earliest moments. The techniques should ultimately allow us to test the fundamental physics that governed the universe when it was less than a second old. The background noise is thought to contain echoes of primordial gravitational waves, ripples in space-time, created by the rapid, massive expansion known as inflation. By precisely charting the slope and intensity of the hum, astronomers can compare the data to different theoretical models. A smooth, gentle curve supports the standard inflationary theory, while a steeper, more complex curve might suggest alternative models, such as those involving cosmic strings. This ability to directly test the physics of creation, answering questions about the very beginning of space-time, represents the ultimate, mind-bending goal of gravitational wave astronomy. The final revelation of the gravitational hum leaves us with the ultimate question: what physics governed the universe at its absolute beginning? As astronomers continue to use our galaxy-sized detector to calculate how we are bobbing up and down in that turbulent sea of space-time, another class of cosmic mystery has emerged, one that involves incredible speed, blinding luminosity, and events that defy every classification we currently have. Every year since 2018, astronomers have spotted a phenomenon that flashes across the sky with mysterious intensity. This explosion is so bright that it makes the average supernova, itself a catastrophic event, look like a faintly lit candle struggling to be seen from a great distance. Some of these events have been spotted relatively close to us, while others are billions of light years away, yet they appear remarkably similar to one another. Despite the mounting evidence and repeated observations, no one is certain what these flashes fundamentally are, or what colossal event could possibly cause them. Through rigorous observation and analysis, astronomers initially began decoding a pattern and formulating tentative, plausible theories. But then, in 2023, they saw a new one, a flash so bizarre it completely baffled them, throwing existing theories into immediate doubt. These explosions have been formally named luminous fast blue optical transients, often shortened to LFBOTs, pronounced LFBOTs. There is simply nothing else like them in the known universe, placing them in a category of their own. Despite their immense power, the sheer novelty of luminous fast blue optical transients, LFBOTs, means our knowledge is still minimal, making a fixed, universal definition difficult for astronomers to agree upon. The first LFBOT was only detected in 2018, and since then, only a handful have been definitively witnessed and studied. However, scientists have successfully identified a set of shared, defining characteristics that place these events in a class entirely separate from normal supernovae. First, they are extraordinarily luminous, displaying an exceptionally high optical luminosity that can be 10 to 100 times brighter than a standard supernova. Second, they are intensely blue, emitting predominantly blue light in the visual spectrum, which indicates extreme temperatures. This thermal intensity also causes them to be powerfully bright across other wavelengths, including X-rays, ultraviolets, and radio waves. Finally, as their name suggests, they are exceptionally fast. An LF bot erupts like a cosmic camera flash, rapidly peaking in brightness and then dimming just as rapidly, often vanishing within the span of mere hours or days, a rate far quicker than the weeks or months required for a typical supernova to fade. The very nature of luminous fast blue optical transients, LFBOTs, their rapid onset and equally rapid fading, makes them exceptionally difficult to capture and study. They are cosmic events measured in mere hours, not weeks or months, meaning traditional astronomical surveys often miss them entirely. Yet, their discovery came not from a dedicated deep space telescope, but from a system initially designed to protect Earth. The pivotal discovery relied on the NASA ATLAS HKO telescope in Hawaii. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a network primarily designed as an early asteroid impact warning system. Its routine and continuous job is to scan the entire visible sky multiple times every night, looking specifically for objects that are moving the telltale sign of a near-Earth asteroid that might be on a trajectory that crosses Earth's orbit. On the 16th of June, 2018, the ATLAS HKO unit was performing its routine scan when it captured something highly unusual and completely stationary, a brilliant, non-moving flash. This flash was an extreme anomaly, a sudden burst of light that was estimated to be 100 times brighter than a regular core collapse supernova. Crucially, the light faded just as quickly as it appeared, vanishing almost entirely within the space of a few days. This fleeting, powerful, blue explosion should have been nearly impossible to catch. Yet ATLAS's continuous, wide-field surveillance, designed to track movement, inadvertently captured this moment of cosmic stillness and power. The moment the alert was issued, the astronomical community mobilized into an immediate global scramble. Scientists worldwide quickly accessed the initial data captured by ATLAS HKO and began an intense, multi-wavelength analysis to understand the nature of the violent event they had just witnessed. Scientists quickly pinpointed the source of the massive, unique explosion, locating it within the celestial boundaries of the Hercules constellation, approximately 180 million light-years away from Earth. The event was formally designated AT2018 COW because the phenomena was so strange, so unlike anything catalogued before. The event was quickly and affectionately nicknamed the Cow, simply derived from the last 3 letters in its official designation. This unusual moniker stuck, as the sheer strangeness and unpredictable nature of the event required a memorable, if slightly absurd, placeholder name. Initial analysis attempted to fit the Cow into the existing framework of known cosmic explosions. Based on its extreme brightness and rapid onset, the event was first quickly classified as a standard Type 1b supernova. A Type 1b is a common kind of explosion, also known as a core collapse supernova, which occurs when a massive star exhausts its nuclear fuel and its core collapses under its own powerful gravity, leading to a catastrophic explosion that temporarily rivals the brightness of an entire galaxy. The initial classification of the event immediately ran into serious problems because the explosion didn't cleanly fit the expected model of any known supernova. When astronomers meticulously examined the COW's emission spectrum, the unique signature of light that acts like a chemical fingerprint, it fundamentally contradicted the typical pattern of a Type 1b supernova. Specifically, the spectrum showed two major deviations. First, it had unusually broad emission lines, signaling that the explosive material was moving outward at speeds far faster than what's seen in a standard supernova blast wave. And second, the event displayed very weak helium lines, a surprising absence since the element helium should have been strongly present and relatively strong in a Type 1b event, which occurs when a star has lost its hydrogen layer, but not its helium. These characteristics made the explosion appear more reminiscent of a Type 1cBl supernova, a category for supernovae that have lost their entire hydrogen and helium outer envelopes before collapsing. Based on this spectral analysis, the COW was hastily reclassified into the Type 1cBl category. But even this new designation was temporary. The more data the scientific community gathered and the more closely they analyzed the explosion's total energy, speed, and asymmetry, the less it resembled any type of supernova they had ever studied. The COW was a true outlier, quickly demanding the creation of an entirely new category of cosmic event. However, the more scientists pored over the data, the more surprised and confused they became. Whatever this explosion was, it began to look less and less like any type of supernova they had ever studied. For starters, it appeared to erupt out of nowhere. The blast went from a completely inactive state to reaching its peak luminosity in just a few days. As we noted, supernovae generally take a few months to reach their brightest peak and then dim again at a similar, slow pace. The COW's speed was unprecedented. Not only was it fast, but it was registered to be 10 to 100 times brighter than an ordinary supernova, placing its total energy output into an entirely new, extreme category. Crucially, everything about the way it exploded was fundamentally wrong for a standard supernova. When massive stars explode as supernovae, they tend to release their energy in a spherical shape, like an expanding bubble. We know that the shock waves sent out after a supernova can sometimes be spherical, not perfectly round, due to the presence of strong magnetic fields within the collapsing star, which can distort the shape of the initial blast. But upon closer inspection, the COW did not just appear slightly spherical. The researchers themselves described it as the most spherical explosion ever seen. It was violently lopsided, suggesting an extreme mechanism that did not release energy uniformly in all directions. This confluence of impossible characteristics, extreme speed, extreme brightness, and extreme asymmetry, made the initial supernova classifications untenable. The event demanded new ideas, and soon enough, other theories were being put forward to explain the mysterious LF-bots. Some theorists suggested the COW could be a monster black hole shredding a passing star, a phenomenon called a tidal disruption event, but one that produced a blue flash instead of its usual light signature. Others proposed it was a supernova that was so powerful and energetic it immediately gave birth to a highly magnetized, rapidly rotating object like a new black hole or a neutron star, and that the energy from this new object was fueling the extraordinary luminosity. The initial classification crisis surrounding the COW highlighted a fundamental obstacle in decoding any new cosmic phenomenon: the lack of data. It's difficult to draw any solid conclusions when you only have one example. As the old adage reminds us, once is an anomaly, twice is a coincidence, and only 3 times is a pattern. What researchers truly needed was a larger sample size, more instances of this type of powerful, rapid explosion so they could compare observations and deduce the underlying physics. Luckily, the universe did not make them wait long. Just a few months later, in September 2018, the cosmic camera flashed again with a second, similar explosion. And then, a third instance was recorded in 2020. Keeping with the tradition of pulling animal nicknames from the last 3 letters of their official designations, astronomers quickly began assembling a small LF-bot zodiac. The cow was soon joined by the koala and the camel. With data on 3 separate LF-bot events, researchers could finally begin hunting for common patterns. One of the first things that stood out to researchers when analyzing the cow, the koala, and the camel was the location of these powerful explosions. Even though the 3 events occurred in widely distant parts of the universe, each blast was unequivocally registered as coming from inside the spiral arm of a galaxy. This location data immediately bolstered the initial, tentative theory that LFBOTs were simply a specialized, extreme type of core collapse supernova. To understand why, we must recall the nature of the stars that cause these explosions. The kind of star that triggers a core collapse supernova is a massive star, one of the largest and hottest types of star in existence. As a rule of stellar evolution, the bigger the star, the shorter its lifespan. These stellar giants burn through their nuclear fuel at a ferocious rate. This means they do not get the chance to travel very far before they exhaust their fuel and die in a supernova explosion. It would therefore make perfect sense that their supernovae occur very close to the dense, dusty star clusters where they were originally born. And what parts of a galaxy are known for having high concentrations of gas, dust, and massive, young star clusters? The spiral arms, the exact place where astronomers had observed all 3 of the initial LF-bots. The location seemed to confirm the hypothesis. LFBOTs were just incredibly bright, fast versions of the familiar supernova. Just as researchers seemed to be making solid progress in classifying LFBOTs, something happened in 2022 that once again caught them completely off guard, undermining the idea of a simple, single explosion. The Zwicky Transient Facility, ZTF, a very wide-angle ground-based camera that continuously scans the entire northern sky every 2 days, much like the Atlas telescope in Hawaii, detected yet another similar LF-bot explosion. This event, however, started behaving rather strangely after the initial blinding flash. Instead of exploding once and fading away into darkness within a few days, like the cow and its relatives before it, this new LF-bot, nicknamed the Tasmanian Devil, continued to produce repeated, short-duration bursts of extreme light. The pulses lasted far longer than expected, extending over several weeks. What made this phenomenon truly perplexing was that each of these subsequent bursts seemed to be just as bright as the original explosion. The total energy released by the Tasmanian Devil over its active period was staggering. It emitted more energy than the combined light of hundreds of billions of stars like our Sunday. The researchers were deeply puzzled, as this pulsating, reigniting activity was unlike anything that had ever been definitively observed in astronomy before. I know the skeptics among you might be thinking, This has got to be due to some kind of technical error, miscalibrated equipment, a fluke in quality control tests, or a simple mathematical mistake. Indeed, the history of science is littered with supposed breakthroughs, or eureka, moments that were later deflated once someone double-checked the workings and found a human error. But this was not one of those moments. The initial detection was so unusual that the data was immediately cross-referenced and confirmed by 14 other telescopes stationed around the world. The collective, independent observations confirmed that the Tasmanian Devil did, in fact, pulsate a minimum of 14 times. The total number of bursts was likely much higher, possibly obscured by the glare of the initial blast or by gaps in observation. Equally surprising was the timing. These mega-powerful pulses were only minutes apart. To scientists, it looked like a star that kept dying violently and then was somehow being revived again and again, only to explode instantly once more. If this phenomenon is confirmed an object undergoing repeated, minutes-apart explosions, it could provide brand new, profound insight into the mechanics of stellar life cycles. So far, the life cycles of massive stars have only been studied as a series of disconnected snapshots of different evolutionary stages. We see a star as a young blue giant, then perhaps we see the remnant as a neutron star, but we have never witnessed the continuous, dynamic process of an object repeatedly entering and exiting the final, violent stages of its death. The Tasmanian Devil offered the first hint of seeing that continuous process unfold in near real time. In short, even though the multiple, continuous bursts of light from the Tasmanian Devil were highly unexpected, there was still some reason to suspect these events could be an extreme, bizarre type of supernova. At this point, none of the observations directly violated the core collapse supernova theory. Perhaps the enormous initial explosion creates a highly magnetized core that then periodically sheds layers of material in these subsequent bursts. The strange behavior of the Tasmanian Devil, with its minutes apart, repetitive explosions, had already stretched the limits of the supernova theory. But it was the next observation that delivered a definitive, fatal blow to the simple idea that LFBOTs were merely super bright stellar deaths. On the 10th of April, 2023, astronomers detected yet another enormous, rapidly fading blue explosion that carried all the unmistakable telltale characteristics of its LFBOT zodiac relatives: extreme speed, intense luminosity, and high blue thermal emission. The event was designated AT2023VWS and was nicknamed the Finch. However, the Finch was not even remotely close to where the supernova theory dictated it should be. The previous LFBOTs, the cow, the koala, and the camel, all originated from the busy, star-forming regions of spiral arms inside distant galaxies. This was the key piece of evidence supporting the supernova theory, but the Finch completely shattered this pattern. The explosion was pinpointed to a region of space approximately 3 billion light-years away from Earth. Crucially, the Astronomical Survey determined that the Finch was located about 15,000 light-years away from the closest known galaxy. It exploded in the middle of nowhere in the deep, cold vacuum of intergalactic space, effectively floating in the vast, empty void between two entirely separate galaxies. This solitary location was a massive, fundamental blow to the leading core collapse theory. If these explosions were genuinely the result of massive stars exhausting their fuel and collapsing, two things must be true. First, the star must have formed in a region with high density of gas and dust, like a spiral arm, and second, it must have died quickly. Massive stars, with their immense fuel consumption, simply do not live long enough to travel 15,000 light-years from their birthplace in a spiral arm and expire in the intergalactic void. One theoretical mechanism proposed that a massive star could be ejected from its home galaxy during a violent three-body gravitational encounter. But even such a scenario struggles to give a star the necessary velocity and lifespan to reach such a colossal distance before dying. The likelihood of a massive star surviving such a long journey to die in intergalactic space is virtually zero. The Finch's existence confirmed that LF-bots must be caused by something far more complex and exotic than a typical, albeit bright, supernova. The event's location demands a mechanism that can produce an immense, rapid blue flash without requiring a massive star that recently formed within a star-forming galaxy. The single observation of a LF-bot detonating in the intergalactic medium effectively removed the entire class of objects from the standard supernova catalog. This transformation changed LF-bots from a strange new type of stellar death into a truly confounding, deep space mystery, forcing astronomers to entertain far stranger, more energetic theories that do not rely on star formation. With the supernova theory now largely discarded, the mystery of LF-bots has shifted toward mechanisms involving extreme gravity or high-speed collisions capable of generating immense energy in the intergalactic void. One leading idea is an extreme tidal disruption event, where a solitary, wandering intermediate mass black hole, a type of black hole measuring hundreds to thousands of solar masses, encounters and instantly shreds a small star. The resulting explosion would be the star's debris rapidly spiraling and accreting onto the black hole, producing the sudden, intense blue flash far from any galactic center. Another key theory involves the magnetar engine, suggesting that the explosion results from the catastrophic formation of a magnetar, an ultramagnetic, rapidly spinning neutron star, which then launches a highly energetic, relativistic jet fueled by its powerful magnetic field. However, this theory still faces the fundamental challenge of explaining how the massive star that formed the magnetar could have existed in the solitary intergalactic space, far from its required birthplace in a star-forming galaxy. The solitary Finch confirmed that LF-bots are powered by a mechanism that is both incredibly potent and location agnostic, making them one of the most exciting and least understood classes of transient event in modern astrophysics. The discovery of the Finch exploding in the desolate vacuum of intergalactic space irrevocably shattered the leading theory that luminous fast blue optical transients, LFBOTs, were simply super bright core collapse. Supernova. The location of the Finch, 15,000 light-years from the closest galaxy, demanded a mechanism that does not rely on a short-lived, massive star. This observation sent researchers back to the drawing board, forcing them to consider two new, highly exotic theories that focus on phenomena capable of existing far from the crowded spiral arms of galaxies. The first theory suggests that the Finch, and all LF-bots, could be the dramatic result of small stars being torn apart by an intermediate mass black hole, IMBH. An IMBH is a hypothetical type of black hole that occupies the middle ground between the two known black hole categories: the small stellar remnant black holes, which are 3 to 100 times the mass of our Sun, and the colossal supermassive black holes, which are millions to billions of times the mass of our Sun. Should they exist, IMBHs would possess a mass ranging from 100 to 10,000 times that of the Sunday. While their smaller and larger relatives have both been conclusively confirmed to exist, this middle child remains purely theoretical. The existence of IMBHs has never been definitively proven, but if they do exist, could these rogue objects be responsible for this elusive light show? Astronomers have used sophisticated computer simulations to model what happens when a star encounters one of these hypothetical IMBHs. The simulations have shown that a star may orbit the black hole as many as 5 times before its final demise. With each successive orbit around the black hole, the star is subjected to immense tidal forces, the crushing differential pull of gravity, and is effectively ripped apart, losing more and more mass. This process is called a tidal disruption event, TDE. Finally, the remaining stellar matter would be violently flung back out into the galaxy at immense speeds, potentially as high as 10% the speed of light. The rapid conversion of this stellar debris into intense radiation, coupled with the high ejection velocity, would be entirely consistent with the extreme speed, high thermal temperature, blue color, and phenomenal brightness observed in LF bots, lending significant weight to this TDE theory. One of the most likely places researchers would expect to find these elusive intermediate mass black holes is within globular star clusters located in a galaxy's outer halo. Galaxies do not simply end at their visible disk. They possess vast, invisible halos made primarily of dark matter, globular clusters, and ancient stars that extend far beyond the main disk and central bulge. These halos are most visible and expansive in spiral galaxies like our own Milky Way. In our home galaxy, the outer halo is enormous, stretching some impressive 1 million light-years from the galactic center. Some scientists hypothesize that it is plausible that the Finch could have been located inside one of these faint, outlying globular star clusters, which are extremely difficult to detect at a distance of 3 billion light-years. If this is the case, and if intermediate mass black holes truly reside within these clusters, it becomes plausible that the Finch was caused by one of these unusually sized, rogue black holes ripping up a large star in the cluster, with the entire cluster being located far out in the intergalactic medium, effectively isolated from the main galaxy. The second major theory put forward by researchers suggested that the Finch could have been the result of 2 highly dense stellar objects, specifically 2 neutron stars moving toward each other in increasingly tight spirals until they Big 6 violently collided and merged. This kind of merger event causes a kilonova, which is known to be one of the biggest and most powerful stellar blasts in the universe, second only to some supernovae. Kilonovae are capable of producing immense blue light flashes that fade quickly, characteristics consistent with LF bots. One critical, telltale sign of a kilonova is the distinct presence of gravitational waves. As the 2 neutron stars spiral toward each other at relativistic speeds, they generate a characteristic gravitational signal known as a chirp. This chirp is caused by a rapid increase in wave frequency as the 2 massive objects accelerate, eventually colliding and merging in the final, powerful release of energy. If astronomers could have found this specific gravitational chirp signature when analyzing the data from the Finch, it would have lent incredibly strong and conclusive credence to the neutron star merger theory. Unfortunately, due to a profound stroke of bad luck, our primary chirp detector, the Laser Interferometer Gravitational Wave Observatory, was completely down for maintenance at the exact time the Finch event occurred in April 2023. This critical technical outage means that we have no data to confirm or deny the emission of gravitational waves during the LF-BOT event. The neutron-star merger theory also faces challenges in the electromagnetic spectrum. Kilonovae often produce short, intense bursts of high-energy radiation known as gamma-ray bursts, GRBs. One thing we do know about the Finch is that no gamma-ray burst was detected by orbiting space telescopes during or immediately following the event. However, the lack of a GRB is not necessarily a definitive refutation of the kilonova theory. This explosion occurred 3 billion light-years away from us, an immense distance. It is possible that the burst was simply too far for the gamma-ray data to be detected, or that the highly focused, narrow beam of the gamma-ray burst was simply not aimed directly at Earth. If the beam was angled slightly away from our line of sight, we would miss the high-energy gamma rays entirely, while still observing the wider, more isotropic optical light. All in all, the missing gravitational wave data and the lack of a conclusive gamma-ray signal mean that none of the available data can yet conclusively confirm or reject the neutron-star merger theory. The uncertainty surrounding such an incredibly rare, powerful, and mysterious new phenomenon is deeply frustrating to the astronomical community. The current reality for astronomers tackling the LF-BOT mystery is a stark lesson. While the technology we build advances rapidly, patience remains an essential and highly underrated virtue. The universe simply doesn't rush its answers. However, scientists aren't passively waiting. They're actively planning the next wave of observations and deploying the most powerful tools available to unlock this cosmic enigma. This strategic planning focuses on two immediate goals: confirming the intermediate mass black hole theory and dramatically broadening the sample size. The primary focus is currently on confirming the bold theory that LFBOTs are powered by a tidal disruption event involving an intermediate mass black hole. The Finch's location in intergalactic space strongly suggests its origin is a rogue object, perhaps one flung out of a galactic core, and IMBHs are prime candidates for such objects. To directly test this idea, scientists are turning to the most advanced instrument ever conceived for infrared observation: the James Webb Space Telescope, JWST. The Finch exploded 3 billion light-years away, making any faint structures around it incredibly difficult to see. But the IMBH theory hinges on the possibility that the black hole resides within an ancient, faint, and highly distant globular cluster, a dense ball of stars orbiting in the galaxy's outer halo. Using the JWST's phenomenal infrared optics and unmatched resolution, astronomers are planning a meticulous search. Their goal is to look for any faint, tiny collections of stars, the potential globular cluster in the exact region of space where the Finch exploded. Finding such a faint cluster, which would be nearly invisible to older telescopes, would serve as a major vindication for the IMBH theory. It wouldn't prove the black hole exists, but it would clarify that astronomers are on the right and plausible physical path. Conversely, if the deep search comes up empty, it would strongly suggest that the IMBH theory is unlikely, forcing the community to lean more heavily on the magnetar or kilonova explanations. In the meantime, other researchers are focused on the original, essential problem of low sample size. The 6 LF-BOTs we've observed so far have taught us immense, unexpected lessons, from their asymmetry and extreme speed to the impossible location of the Finch. But 6 data points are simply not enough to confidently confirm a pattern. nor to rule out subtle variations in the explosions. We have much left to learn about the energy distribution and host environments of ELF bots. The only way we are going to get a large enough sample to confidently decode the pattern, or the lack thereof, is to drastically increase our surveillance. We must continue sweeping the entire sky with wide-field transient surveys capable of spotting these fleeting flashes before they disappear. Scientists' greatest hopes are currently pinned on the Vera C. Rubin Observatory, currently nearing completion in Chile. This revolutionary telescope is not designed to stare deeply at small sections of space. It's designed to perform the Legacy Survey of Space and Time, LSST. This monumental survey will continuously scan the entire southern sky every few nights, creating a massive, deep record of cosmic change. The Rubin Observatory boasts a huge mirror and an advanced camera that will be able to capture 10 times more light and survey the sky far faster and deeper than all previous facilities combined. Its rapid, deep scanning capability is ideally suited to catch these fleeting, fast blue transients. The sheer volume of data it generates will transform our search, potentially turning LF bots from a handful of anomalies into a robust statistical population, finally allowing for proper classification. The detection of an LFBOT by the Rubin Observatory is only the first step. The overall strategy relies on immediate follow-up observations using an array of instruments. Once a new flash is detected, time becomes the enemy, and the world's most powerful telescopes must pivot instantly. The powerful ground-based telescopes like those in Hawaii and Chile, and the orbiting Hubble Space Telescope will be used to analyze the light in greater, multi-wavelength detail. This follow-up is critical for spectral analysis. Detailed examination of the light spectrum can confirm the explosion's temperature, velocity, and elemental composition, helping to distinguish between the debris of a shredded star, TDE, and the nuclear material from a neutron star merger, kilonova. Host environment, determining if the LF bot is truly alone or if it's connected to a faint, hidden host galaxy or cluster. LFBOTs are a super new phenomenon that we still do not understand well. Scientists themselves readily admit that the discovery of the Finch fundamentally changes our understanding of what constitutes a normal explosion in the deep cosmos and raises far more questions than it answers. But with tools like the JWST and the Rubin Observatory coming online, we are perfectly positioned to finally answer this profound mystery. The more we learn about these intense, bright blue explosions, the more they defy simple classification and keep surprising us with their exotic locations and behaviors. The mystery of the luminous fast blue optical transients, LFBOTs, is a powerful reminder that the universe still holds vast, unexplained phenomena. All there is left to do is what hundreds of generations of astronomers have done for centuries before us: point our telescopes up to the sky, watch, and wait. But waiting today means listening not just with light, but with an entirely new sense, the sense of gravity. The story of listening to the cosmos through gravity began over a century ago. Back in 1916, Albert Einstein published his general theory of relativity, which fundamentally predicted that massive, accelerating objects like two black holes spiraling toward each other must radiate energy outward in the form of gravitational waves. To visualize this, imagine throwing a heavy rock into a perfectly calm pond. The water surface ripples, expanding outward in circles. You can think of gravitational waves like those ripples, except instead of acting on water, They act on the very fabric of space-time itself, ever so slightly stretching and contracting it as the wave passes. Einstein predicted that these disturbances would be so incredibly small that even he, the father of the theory, did not think humans would ever be able to detect them with any instrument. Fast forward to today. In just over a century, humanity has managed to overcome Einstein's pessimism. We've managed to build an astonishing global network of observatories that have picked up on gravitational waves from about 100 cosmic events. This network has opened up a new era of astronomy, allowing us to hear the universe's most violent moments. The core of this gravitational detection system relies on 3 major observatories that work together in perfect synchrony to confirm data and pinpoint the wave's direction and source location. These observatories are the Laser Interferometer Gravitational Wave Observatory, LIGO in the United States, Virgo in Europe, and Kagra in Japan. If you aren't familiar with their setup, the way these instruments work will surprise you because they are nothing like traditional telescopes. They don't use large mirrors or lenses to gather light. Instead, they rely on something much more fundamental and fun: lasers and geometry. Scientists at each observatory send powerful laser beams down 2 perfectly perpendicular vacuum tunnels that are several kilometers long. These tunnels form a perfect L shape. The lasers reflect off mirrors at the end of each arm and return to the starting point where they are compared against each other. When a gravitational wave arrives at Earth from space, it causes tiny, subtle disturbances in the fabric of space-time. As the wave passes, it momentarily stretches the length of one arm while simultaneously contracting the length of the perpendicular arm. And when we say tiny, we mean almost unbelievably small. The actual distance change that these instruments are designed to detect is approximately 10 to the power of minus 18 meters, which is about 1/10,000th the width of a proton. As the laser light paths are stretched or contracted by the passing gravitational waves, the waves of light within the tunnel emit different frequencies when they recombine, much like the strings of a guitar being momentarily stretched or loosened. A longer, looser string produces a lower frequency, a lower pitch, while a shorter, tighter string produces a higher frequency, a higher pitch. This shift in frequency is the raw data of the gravitational wave. Scientists convert this raw frequency data into a format that the human ear can perceive, and this conversion reveals the unique acoustic signature of a cosmic event. This signature is often a rising, sweeping sound known as the chirp of a black hole collision. Each collision has its own distinct personality encoded in the sound. For example, a long, low build-up that gradually increases in pitch and volume indicates a slower collision between 2 relatively lightweight black holes. The slow build-up represents the time the black holes spent orbiting each other hundreds of times before the final, rapid merger. In contrast, the collision of faster, heavier black holes sounds more like an immediate, sharp thump or a rapid screech. One of the most remarkable sounds ever recorded was an event known as GW 150914, the first ever detection. When you listen to it, you are hearing the sound of 2 black holes, one 36 and the other 29 solar masses combining to form an even bigger black hole 5 billion years ago. It was the most massive and distant gravitational wave source ever observed at the time, emitting the energy equivalent of about 5 solar masses in pure gravitational radiation. This immense conversion of mass directly into energy is an epic confirmation of the power locked within Einstein's most profound equations. The final fate of the LF bots whether they are powered by unseen intermediate mass black holes or high-speed neutron star mergers, will undoubtedly be revealed not just by the light we see, but by the gravitational ripples we can now hear. The more we learn about these intense, bright blue explosions, the more they defy simple classification and keep surprising us with their exotic locations and behaviors. The mystery of the luminous, fast blue optical transients, LFBOTs, is a powerful reminder that the universe still holds vast, unexplained phenomena. All there is left to do is what hundreds of generations of astronomers have done for centuries before us: point our telescopes up to the sky, watch, and wait. But waiting today means listening not just with light, but with an entirely new sense, the sense of gravity. The story of listening to the cosmos through gravity began over a century ago. Back in 1916, Albert Einstein published his general theory of relativity, which fundamentally predicted that massive, accelerating objects like two black holes spiraling toward each other must radiate energy outward in the form of gravitational waves. To visualize this, imagine throwing a heavy rock into a perfectly calm pond. The water surface ripples, expanding outward in circles. You can think of gravitational waves like those ripples, except instead of acting on water, they act on the very fabric of space-time itself, ever so slightly stretching and contracting it as the wave passes. Einstein predicted that these disturbances would be so incredibly small that even he, the father of the theory, did not think humans would ever be able to detect them with any instrument. Fast forward to today. In just over a century, humanity has managed to overcome Einstein's pessimism. We've managed to build an astonishing global network of observatories that have picked up on gravitational waves from about 100 cosmic events. This network has opened up a new era of astronomy, allowing us to hear the universe's most violent moments. The core of this gravitational detection system relies on three major observatories that work together in perfect synchrony to confirm data and pinpoint the wave's direction and source location. These observatories are the Laser Interferometer Gravitational Wave Observatory, LIGO, in the United States, Virgo in Europe, and Kagra in Japan. If you aren't familiar with their setup, the way these instruments work will surprise you because they are nothing like traditional telescopes. They don't use large mirrors or lenses to gather light. Instead, they rely on something much more fundamental and fun: lasers and geometry. Scientists at each observatory send powerful laser beams down two perfectly perpendicular vacuum tunnels that are several kilometers long. These tunnels form a perfect L shape. The lasers reflect off mirrors at the end of each arm and return to the starting point where they are compared against each other. When a gravitational wave arrives at Earth from space, it causes tiny, subtle disturbances in the fabric of space-time. As the wave passes, it momentarily stretches the length of one arm while simultaneously contracting the length of the perpendicular arm. And when we say tiny, we mean almost unbelievably small. The actual distance change that these instruments are designed to detect is approximately 10 to the power of -18 meters, which is about 1/10,000th the width of a proton. As the laser light paths are stretched or contracted by the passing gravitational waves, the waves of light within the tunnel emit different frequencies when they recombine, much like the strings of a guitar being momentarily stretched or loosened. A longer, looser string produces a lower frequency, a lower pitch, while a shorter, tighter string produces a higher frequency, a higher pitch. This shift in frequency is the raw data of the gravitational wave. Scientists convert this raw frequency data into a format that the human ear can perceive, and this conversion reveals the unique acoustic signature of a cosmic event. This signature is often a rising, sweeping sound known as the chirp of a black hole collision. Each collision has its own distinct personality encoded in the sound. For example, a long, low buildup that gradually increases in pitch and volume indicates a slower collision between two relatively lightweight black holes. The slow buildup represents the time the black holes spent orbiting each other hundreds of times before the final, rapid merger. In contrast, the collision of faster, heavier black holes sounds more like an immediate, sharp thump or a rapid screech. One of the most remarkable sounds ever recorded was an event known as GW 150914, the first ever detection. When you listen to it, you are hearing the sound of two black holes, one 36 and the other 29 solar masses, combining to form an even bigger black hole. 5 billion years ago, it was the most massive and distant gravitational wave source ever observed at the time, emitting the energy equivalent of about 5 solar masses in pure gravitational radiation. This immense conversion of mass directly into energy is an epic confirmation of the power locked within Einstein's most profound equations. The final fate of the LFBOTs, whether they are powered by unseen intermediate mass black holes or high-speed neutron star mergers, will undoubtedly be revealed not just by the light we see, but by the gravitational ripples we can now hear. The journey we have taken today, from the quiet hum of the ancient universe to the blinding flash of the newest cosmic explosion, shows us that the way we explore space is fundamentally changing. We are no longer limited to observing the universe through the visible light that has guided astronomers for millennia. We have unlocked an entire new layer of the universe. First, by building detectors like LIGO, we gained the ability to hear the high-frequency bangs of stellar mass black hole collisions, revealing a universe far more violent and dynamic than previously imagined. We learned that the very fabric of space-time can be warped and stretched by forces greater than the light of billions of stars combined. Second, by cleverly utilizing the pulsar timing array, we gained the ability to hear the low-frequency hum of the most massive objects in existence, the supermassive black hole binaries. This hum is a direct window into the evolution of galaxies and, potentially, an echo of the universe's creation itself, allowing us to peer past the 400,000-year-old curtain of the cosmic microwave background. These gravitational observations give us evidence of incredibly remote and ancient phenomena that simply cannot be measured by other means. They are also a crucial, secondary way to verify and strengthen observations made by light-based instruments like the Hubble and James Webb Space Telescope. By combining light and gravity, by engaging both our sight and our hearing, we are moving into the age of multi-messenger astronomy. In time, this revolutionary field should allow us to fully understand the intricate nature of our universe, charting its complete history, from the initial burst of inflation to the ultimate destiny of its most massive galaxies. The LFBOTs are merely the latest, most exciting question mark on the new map. We are prepared for the coming discoveries. Tune into the universe with the right equipment, and you will hear it humming, vibrating, and thundering with power. No matter where you look in the sky,